Okay, last optimization question. Suppose you work for Campbell Soup. Suppose you're working for Campbell Soup and they want you to make soup in half-liter containers, 500 milliliters. What would the ideal radius of the can be to minimize the cost or not, or to minimize the amount of material? Okay. Again, oversimplified question. There are obviously lots of factors, and I'll talk a little bit about that when I'm done. But again, basic situation here. Suppose you're selling soup in a half liter, or what we call 500 milliliter cans. What would the optimal radius be to minimize the amount of material needed to make the can? So again, we have our can, and the volume of a can is pi r squared h. You might not remember that, but that's from geometry, but it is. It's pi r squared h, and we want that to be 500. That's going to be important to us. We can actually kill two birds with one stone in a second. Now, the question is, we want this to be 500 milliliters, but we want this to be the least amount. We want the area of the material to be the least. And so if you look at a can, the can has a lid and a bottom, which are both circles. Circle has areas of pi r squared, just in case you forgot. I don't think you forgot that, but it's pi r squared. But there's two of them. There's one for the top, one for the bottom. Now the one that's not as obvious is what we call the lateral area. If you took a can opener and you took the top off, and you took the bottom off, and then you took a scissors and went up the side of the cylinder and unraveled it. Remember, this is wrapped around the circle, so this distance here is the circumference, which is 2 pi r. That's another formula you have to remember from geometry. And then, of course, this is the height of the can. So what would the area of that material be? That would be 2 pi r times h. So this is the area. Now here's the thing. We're trying to find the optimal radius. We don't want the height in the equation. Not that I could have asked for the height, but I didn't, okay? So how am I going to do this? Well, I'm going to kill two birds with one stone here. Kind of cool. And you might miss it if you didn't catch this. If I didn't make, sorry, you might not catch it if I didn't make a big deal about it. This is the area of any can. That's the surface area of any can. Any can's got a top, a bottom, and the lateral area. What we're going to do is we're going to kill two birds with one stone. We're going to get rid of the h, and we're going to make it so this is not an area of any can, but an area of a can that holds precisely 500 milliliters. Now you might go, Mr. Peters, how come you changed it to cubic centimeters? Hopefully you learned in science class that 1 milliliter is 1 cubic centimeter, right? Okay, so that's kind of cool, right? So we can go from this liquid milliliter to surface area, to area, right? We can go to centimeters, right? So in case you've forgotten that, 1 milliliter is exactly 1 cubic centimeter. So I have 500 cubic centimeters. If I divide by pi r squared, I can actually get h in terms of r. So where that h is right here, I'm going to put this in for h. So what do I get then is the area in terms of the radius, and this is the big deal, for a can that holds precisely half a liter, it would be 2 pi r squared plus 2 pi r times 500 over pi r squared. So let's clean this up here a little bit. Let's see, the pi's will cancel, one of the r's will cancel, so what I get, 1,000 over r. Now trust me on this next step. Bring the r upstairs as a negative 1 power. It'll make that way you don't have to do a quotient rule, right? You can just do a power rule. So this is the area in terms of any r. So I could make the r anything, and I could figure out what the area would be for the amount of material I needed. But I don't want any area. I want the least area. I know how to do that. Remember how we find the least of a function? We've been doing that for the last couple weeks, right? How do you find the least of a function? You figure out when its derivative equals 0. Then we're done. So we know that what I need here is I need to figure out when the derivative of this equals 0. Now, take the derivative here. So 4 pi r negative 1,000 r to the negative 2. Now I have to figure out when that equals 0. Now it's going to require a little bit of algebra here. Move this over to the side. 4 pi r. Cross multiply. I'm running out of room here, so I'm going to move over here. 1,000 equals 4 pi r cubed. Divide by 4 pi. 1,000 over 4 pi equals r cubed. So r would be the third root of 1,000 over 4 pi. Now, if you want, you can simplify that and make it 500 over, oh, actually, no, it goes, you can make it 250 over pi. You don't have to. I'm okay with that answer. Since you have access to calculators, you could actually, get a, let me do that. Well, what would that be in terms of a decimal? Because you might want that, 250. Remember, I wouldn't normally do this during class, because I'd make you, 4.3, about. It's approximately 4.3. Now, if you put the 4.3 back in over here, what comes out? So let me store that in. Now, normally I would show this on the calculator, but I'm running out of space and stuff here at the house. So you're gonna have to trust that I'm doing my calculation right here. Oh crap! I made a mistake. Don't trust my calculation. What's weird is the height is exactly double that, 8.6. And if you go in your pantry and look at almost any can, like Campbell's Soup's can or anything like that, you'll notice that the height is almost exactly the same as the diameter. Almost always. Okay. Now, you notice that it's not always, though I can think of a lot of counter examples. Yeah. Okay, guys. Here's the idea. I want to kind of show through these two examples, the lighthouse example and the can example, that optimizations and this idea of min-max is a really important idea in economics. If you want to make cans, you want to make them as cheap as possible, right? I mean, if you're going to put soup in cans, you don't want to make the cans expensive. So it turns out that if you want to get precisely half a liter of soup in this can, the ideal radius is 4.3 and the ideal height is 8.6. So you only have to find the radius. Now, you might go, but I don't always see it that way. Yeah, you guys, there are a ton of factors. One of the first things they do, like if you're in your first year engineering class, when they give you this type of question, the first thing they'll point out is, how do they make cans? How do they get those circles? What they do is they stamp them out. Like they have sheets of metal going through the machine. And they stamp out. But what happens is all this gets wasted. So the first thing you learn in engineering is you wouldn't use this to minimize costs to start with. What you would do is you'd actually have to realize, well, that's going to be wasted anyways. So really, I need to use squares instead of circles. Because I'm going to lose that. That's still part of the cost, right? I've got to pay for that stuff I throw away. So that's one thing. The other is, Mr. Peters, what about Coke cans and Pepsi cans? They're taller than the diameter. Yeah, but if you look at a can of Pepsi and Coke, notice that the thicker metal is on the top. And the thinner metal, like you poke the sides, it's pretty thin metal, but the metal on the top is a little bit thicker. Well, if it costs more to make tops than it does to make the side, you're going to want to shrink the tops a little bit more, right? Oh, Mr. Peters, what about tuna cans? Yeah, you also have to keep track of what you're putting in the cans, right? If you're putting meat, like tuna, like fish in the cans, if you make the cans too high, the pieces of fish at the bottom of the cans get smushed by the pieces on the top. You don't have that problem with liquids, right? With soup or motor oil or something like that, right? So one thing to keep in mind is there's a lot of factors that go into optimization. In these two examples that I've done, I've really oversimplified the process. But what you want to realize is that there is an ideal radius, in this case, to make a can that would hold the most amount of soup with the least amount of material. Now, the least amount of material doesn't always mean the same thing, and what you're putting in the can matters, and there are a lot of cost of production matters, like this, our tops more than the sides. But anyways, that's the basic idea here, is that what we're doing is you're figuring out when the derivative is zero. Now, just kind of to oversimplify this idea, is for all of my optimization questions that you have, it will always be when the derivative is zero. It's not going to be at the endpoints. Okay, so let that go. You don't have to check endpoints if you don't want. There's a specific reason for this one, because there is no endpoint, right? Because I can make the radius really big. I can make giant lids, right? Or I can make the height almost infinity. And there's a theorem that we're not going to get to that kind of has a way of dealing with that. That's not just checking the endpoints, because what do you do if you have an open interval? Because remember, the whole point here, you had to have a closed interval. But we're going to just kind of end here, okay? I still think that fundamentally that is the biggest deal here. The answers are almost always at the critical number. So, and again, this idea is a big deal. A lot of manufacturing and things that are in motion are all predicated on this type of stuff, of what we call optimization. Okay.